Hey everybody, here we are. Got a technical one for you today. This thing's called chi-square. Chi-square is a tool that lets us mathematically tell whether the difference between two, three, four, or five things or more is statistically significant. The sign for chi-square looks something like that. It's an exaggerated x, a little square sign too. Now it's chi-square, not chi-squared. This isn't a function, it's a symbol. All right, so you don't have to do anything with the squaring part. It's just a symbol as it is. Before we start talking about how to use it, we have to get a sense of how it's going to be used. When you're comparing groups in science, you have to start with the assumption that whatever you do or whatever experimenting you're doing, there's really not going to cause a difference. And there's a reason for that. If we approached everything in science as if I do this, then it's going to change that, then we're sort of putting our conclusion in front of the evidence. Instead, what a null hypothesis allows you to do is objectively and unbiasedly stand back and say, I don't think this is going to have any effect. Let's see what happens with the evidence. So to start with a null hypothesis, you would say cats don't prefer one food or the other. No matter what color light I use, it's not going to make a difference. And age has nothing to do with music ability. We write it as that, as a zero for hypothesis. And just to be clear, whenever you write a hypothesis for a null hypothesis, you just say conditions will have no effect, or I hypothesize that the conditions will have no effect on the outcome. You can, however, after you've stated your null hypothesis, say something about an alternative hypothesis. That maybe my alternative hypothesis would be maybe cats prefer a fish tasting food or snack versus a beef tasting one, or this kind of light because it's red and I know something about photosynthesis will have a greater effect on plant growth than this color light, and so on. For those, you just write your hypothesis with a 1. And you can have many alternative hypotheses. They can keep going on 1, 2, 3 as you number them. You might want to do a number of experiments at once. So I set up sort of a bogus experiment for us to get our feet wet with. So here I have a field, and in there, crop 1 is going to get heavy nitrogen, crop 2 is going to get heavy potassium, and crop 3 is going to get heavy phosphorus. My null hypothesis would be there's going to be no effect with the different nutrients that I'm adding to the plants. I could say, as an alternative hypothesis, I do believe that fertilizer 1 could cause the plants to grow taller because I know that nitrogen goes into making proteins, and you would include a because. You're not going to willy-nilly throw it out there and hope that it happens. Now, at the end, what kind of evidence should that look like, right? If we go back to beginner bio and you had a little graph like this, and one plant grew that tall and one plant grew that tall, you're like, yes, see, there is a smidgen of more growth. So clearly this one worked better than that one. We have to be a little bit better of a critical thinker when it comes to this. So here's what I have for you. Let's look at a simple table. Let me reset my numbers. You may recognize this. Observed minus expected divided by expected. That's percent error. You've done that before. But here's where it gets a little interesting. Sometimes you can have a negative percent error, positive percent error. By squaring it up top, you're going to just create absolute numbers, no positives or negatives. So observed minus expected squared divided by expected will give you a value. Now let's look at what happens here. We've got 100 is my expected value, and that 100 could have come from previous experiments. It could be something I know. I'll teach you how to do an expected a little later. But at some point going into this, you got to know what to expect. I'm calling it for our bogus experiment a 100. And the observed height after you ran the experiment for fertilizer 1 with nitrogen was also 100. And you'll notice that there was 0 at the end. If I take my observed minus my expected and I square it divided by expected, it's 0. And if I sum all of those differences up at the bottom, I'm still left with 0. This value I have highlighted is called your chi-square. Watch what happens. Maybe the nitrogen did work pretty good and it grew a little taller. Maybe the phosphorus, I'm sorry, I guess the potassium was pretty good too. So maybe that's 105 and 105 and then maybe 99. I don't know. See what's happening in my chi-square? Every time I get a little farther away from my expected, the chi-square goes up. Every time I get a little farther away from my expected, chi-square goes up, right? Why is that? It's because it's collecting the differences that are happening between what you expect and what you're actually seeing. And we have to know that in the real world, there's going to be some differences. You're not going to stay perfectly in line with what you expect. So we have to provide some leeway. But at some point, there's going to be a threshold of what is acceptable and what is not. So if I go to a graph and I'm like down here with my chi-square collection of numbers, all those little differences, I have different delineations that number could be. So maybe if that chi-square gets this high, and this is my threshold for accepting the differences, you can see that it hasn't. Maybe my threshold, or I'm sorry, maybe my chi-square is a greater number and it goes over the threshold of the number I've set for accepting it as evidence. Then I would accept it. Chi-square is essentially doing that. It's building up a number so that it gets to a certain point that you can say, yes, it has had a difference, or no, it hasn't had a difference, so that you don't just get to look and stand back and qualitatively say, I guess it's a little greener, or I guess there's more, or if it was me, I'd say yes. It's a number. It allows you to have something quantitative. So a little thing about probability. Nothing in this world is certain, but also nothing is very uncertain, 100% uncertain. And on the left-hand side in green are percent certainties, and it's accompanying uncertainty. So for things that are 30% certain, you can easily say that they're also 70% uncertain. If I turn it into their decimal form, into their proportion form, into their ratio form, 0.3 and 0.7 are, they're correlated. So if I were to say I have a new vaccine and I'm 60% certain it works, you could also say I'm 40% certain it doesn't work, right? You could say I'm 90% certain that it works, but there's a 10% chance that it doesn't work. Well, in this world of biology, we're concerned with the bottom half. In fact, even the 90%, our cutoff is right around there. And anybody who's had statistics knows what I just circled. In biology, we set the 5% as the baseline. And it's not 5% as is. 5% uncertainty is really like saying I'm 95% certain. All right. Now, these become what are called our p-values when we start amassing our evidence about the chi-square. If you want to be really, 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 really certain, you can say I'm 99% certain, which has a p-value of 0.01. If you're wondering where the 0.01 comes from, it's just 1 minus the 99% certainty. Okay, now let's go back to our experiment. These were numbers that I put together in an experiment I never conducted. And these were the numbers that I came up with. So this is a sum of my observed minus my expected squared over my expected. 1.96, 1, and then 0.36. And there's a symbol in algebra called the sum bracket. And if I add all those up together, 3.32 is my chi-square for this particular experiment. And you might be still asking yourself, what in the world is this meaning? I'm not there yet. I'm not there yet. Let's take a look. We always say we start with 0.05. That's our cutoff probability. We want to be 95% certain. The next thing that we do is we look at how many different conditions we used. And collectively, there were 3. We call those threes degrees of freedom. And the way you calculate your degree of freedom is you take how many categories, labeled N, and you subtract 1. So mental math, 3 minus 1 equals 2. All right? So my degrees of freedom up here are 2. The last thing I have to do is act as a little graphing coordinate and look where these two line up. And this number 5.99 shows up. 5.99 in that initial graph I talked about is your threshold. I'm saying that when I add up my chi-square, the addition of those numbers together, the little differences, they have to be greater than 5.99 for me to accept that my null hypothesis is incorrect. Because remember, we're saying there isn't a difference. Now my chi-square value was 3.32. What does this mean? Since my chi-square value is less than the critical value for the probability and degrees of freedom, it means that I accept my null hypothesis, that there really wasn't that much of a difference caused by the different fertilizers that I used. These little differences are not big enough differences to say, yes, the nitrogen, the phosphorus, or the potassium had that great of effect. It's a useful tool. We used to do this experiment until Mars, the company who owns M&Ms, stopped playing along with us. There is a specific percentage of colors that they used to use for their M&Ms, and they are 23%, 23%, and so on. You can see the percents of my expecteds. I made it out of 100, so it was nice and easy. Students would then open up a bag, and we would pour out all the M&Ms, and we would start counting. It was a horrible experiment, and it tasted delicious. We would add up, we would, of course, add up and find our expecteds, but this is simple out of 100. We would do our observed minus the expected squared divided by the expected. And what did we come up with? We came up with these little tiny differences in between what we expected to see as a color and what we actually found in the bag as a color. So you add up all these, right? We get 4.19. How many degrees of freedom do I have? Well, I'm looking at 1, 2, 3, 4, 5, 6. My N equals 6. My degrees of freedom are N minus 1. So 6 minus 1 mental math is 5. So my degrees of freedom are way over here with 5. And then if I look at 0.05 and I look at where they come together, 11.07 is my critical value to overcome this, the threshold number that my chi-square has to be greater than. In this experiment, it was only 4.19. Therefore, I accept. My alternative, my null hypothesis that there was no statistical difference between what I expected to find in M&Ms and what I observed. Okay, let's try this one for real. Here is something similar to what you could see on an AP exam. They will always give you the table to work with. You'll have it in a little legend sheet. They'll give you some information to start with. This, it might be even in the form of like a puzzle that you have to put together, but I'll help you through this. We start with what's called a dihybrid cross between red-eyed normal winged fruit flies. Red-eyed is one trait, normal winged is the second trait. It's a dihybrid cross, which means there's two heterozygous traits being crossed. So because they said red eye is the heterozygous trait, you know that the red is going to be the dominant. It's being expressed. All you need is one allele there. And the normal wing 2 is being expressed. So that's my heterozygous dihybrid. I'm going to cross two of these individuals. Stressed it last chapter that when I have a monohybrid cross, you're going to have that 3-to-1 ratio in the phenotypes. If you have a dihybrid, you're going to have a 9-to-3-to-3-to-1 ratio in phenotypes. 9 of them are 9 dominant, 3 dominant recessive, 3 recessive dominant, and the last 1 recessive. There's no difference in this table. Red eye normal should be in a 9 proportion, 9/16. Red eye should be 3. White eye in normal wing should be 3. And then curly wing, I'm sorry, white eye curly wing should be 1. Another way to say this is it should be dominant, 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 recessive, recessive, dominant, or recessive, recessive. That's the way it should be. Mendel isn't going to follow Mendel's rules all the time. Genetics is a lot more complicated than an 1850s monk figured out. He got us started, but man, it gets really, really, really stinking complicated. Using a chi-square, we can detect right off the bat as to whether we're dealing with something that's Mendelian, Mendel, or if it's something different, which means we have to change strategies on how to understand it. We can use chi-square to do that. So, to start with, let's figure out our expecteds. We already sort of know how to do it because I know that up here, out of 16, 9 behave, 3 behave, 3 behave, and 1 behave a certain way. All I have to do is take 9/16 of 1,211, the total that I'm working with, and that'll give me a value. 3/16 of 1,211. 3/16 of 1,211. And 1/16, it's getting late, 1,211. What do those numbers come out to be? All right, I'm on to something. I've got some stuff plugged in, man. The last thing I have to do before I start calculating anything is over on the right-hand side, let's figure out what we're dealing with. I always like to do my degrees of freedom first. I have 1 group, I have 2 groups, I have 3 groups, I have 4 groups. N minus 1 is 3, right? My 4 groups minus 1 is 3. And we're going to use the 0.05. And that means my critical value is 7.81. I'm going to write that in right here. For a null hypothesis, I'm going to say that there will be no statistical difference between observed and expected in this dihybrid cross. With a critical value of 7.81 and a p-value of 0.05. That is pretty good. I've said there's not going to be a difference, and this is how I'm measuring how much of a not difference there's going to be. Is that, if that makes any sense in your world? Go ahead. You remember observed minus expected squared divided by expected, and then you just have to sum all these guys up down through. I'm going to take a break. Actually, I'm just going to take a sip. Pause the video, do some math, and I'll see you in a second. All right, here we go. See how your numbers turned out. My chi-square is 12.67. My observed minus expected squared divided by expecteds, here's where they are. I sum them all up. So then I look, and my chi-square is greater than the critical value of 7.81. So what does that mean? My conclusion is that I have to reject my null hypothesis because, and I'm running out of room, I would say this better, the chi-square value of 12.67 is greater than the critical value of 7.81. Now you're probably asking for the last time, why? Why? There's a number of good reasons why. Now that we know that these numbers are out of whack, there might be something else going on. Let's investigate. That's what the next chapter is completely about. And I'm telling you right now, when you see things like this, like, oh, that doesn't match, and you repeat it and it doesn't match. It doesn't fit what I want it to. This is where great scientists are born. Studevant was the one who saw that, hey, these numbers don't always match up, and they always seem to match up a certain way other than what we're expecting. He discovered something that you've been talking about for the past month and not even known it. It's really cool. It's really cool. All right. How about a multiple choice, and we'll wrap this up. Researcher observes that two heterozygous plants with red flowers are crossed. The resulting offspring include plants with red flowers, white flowers, or pink flowers. Boom. Ooh. Red, white, pink flowers. Yeah, it's 3. Researcher proposes a null hypothesis that the flower color is the result of independent assortment and complete dominance. The researcher calculates a chi-square of 7.3, assuming 2 degrees of freedom. Okay, now in here, they told you how many degrees of freedom. If they said that there were 3 groups, then you have to do the math yourself. But they've already assumed you the degrees of freedom. So here we are, up here, boom, shakalaka, boom. And we're always using 0.05. We are, should I be assuming? Following is the correct interpretation. Ooh, right there, 0.05. I was right. Not that it's a big deal. So my critical value is 5.99, which means summing up the differences in chi-square has to be lower for me to accept than 5.99 for me to accept my null hypothesis. Let's look at some choices. The null hypothesis should be rejected because the critical value is less than the calculated value. Well, is it? My null hypothesis said there wouldn't be a difference. And I should reject that there is no difference because my critical value is less than the calculated value, the chi-square. So if my chi-square equals 7.3, this exceeds the threshold of evidence I needed for my critical value. So we don't need to go any farther. A is the answer. We can investigate. The null hypothesis should not be rejected because the critical value is less than the calculated value. No, if the chi-square is over, you reject, right? Null hypothesis should not be rejected because the critical value is greater. No. And the null hypothesis should be rejected because the critical value is greater than the calculated value. Critical value is not greater in both cases than the calculated value of chi-square. I hope these helped, and we're going to have some practice in class. If you have any questions, you know how to get a hold of me. Hope this helped. Talk to you guys soon.